State road. Hill. Betancourt. Brown. Browning. Burnett. Here. Davis. DeGraw is here. Herringer is here. La Bounty is here. La Fortune. Douche. McFadden is here. O'Brien. Rodriguez. Scalf is here. And Worthling. All right, so chapter 5 deals with gases. And again, the topics that we're going to cover for the most part, with a couple of exceptions, are topics that you would have covered already in your introductory or high school chemistry. So let me share my screen first. And let me bring up or publish chapter 5 assignment. All right, so this is chapter 5. And the first question, well, let me ask you this first before I start with this assignment. So based on the videos I've posted, are there any questions you guys have that you want me to deal with before we actually get into the assignment? Any questions?
I have a question.
Yes, ma'am.
Are we always going to round the R value to 0.0821?
Good question. Yes. For all purposes, the value of R, and by the way, there are two actual values of R. I'm going to talk about the other one, but the one for now that we'll be looking at and using is 0.0821 liters atmospheres over mole Kelvin. Right, so that's the R value that we're going to use. There's another one which is 8.31 joules per mole Kelvin. So you see here that the numerical value changes because the units change, right? Whereas here we have liters atmospheres here, that is replaced by joules, and therefore, numerically speaking, there's a transformation from 0.0821 to 0.831, all right? So for the most part, we'll be using this value, but later on in this chapter, you'll see where you'd have to use the other one, all right? Okay, any other questions? Yes, sir.
Do you have to decide like paper?
Oh, yeah, what could I forget? So. Right here. Okay, any other questions? Any other questions? Okay, somebody's asking something in chat. Is the assignment published in Canvas? Yes, I just did so. So you should be able to go there and get access to it. All right, so the first question deals with converting some pressure values into other units, right? And basically, let me give a brief discussion, even though this was covered in the lecture. Basically, as far as pressure units go, there are different units, the atmosphere units, you have the Pascal units, you have the torr units. So 1 atmosphere is equal to 760 torr, which is the same thing as 760 millimeters mercury. And I discussed the how the millimeter mercury unit came to being. This is also equal to 101.325 kilopascals. You don't need to memorize these because these are provided, or these will be provided, you know, for your tests and exams and so on, right? And I think those are basically, this is the same thing as, by the way, 101, 325 pascals. And I think that's pretty much all the units for pressure that you're gonna encounter in this chapter. So when number one asks you to perform the following conversion, and the first one is 0.357 atmospheres to torrs, very similar to other types of conversion that you'd have done. So you start off with 0.357 atmospheres, and you multiply by the conversion factor, which relates the atmosphere unit to the torr unit, right? So basically, you're going to put 760 torr above in this conversion factor and divide by 1 atmosphere below, and the atmosphere units will cancel out, and then you do the number crunching. So that would be 0.357 times 760. Well, do this at 0.357 times 760. And according to my calculation, this works out to be equal to 271 total. All right. And that's pretty much what you're going to do for all of these, right? So I don't think I need to do these now unless you have some difficulty with them, but pretty much that's what number one is all about, converting from one unit of pressure to another. All right. Okay. Let me clear this here and scroll down to the next question, which deals with a situation where you have different situations actually. Excuse me, 3 different situations where you have a U-shaped tube in each case. Now there's some differences. The first one, both ends are sealed, right? The second one end is sealed and the other end is open to the atmosphere. And the same is true for this one. But the mercury levels are different in these last two. So we're going to get into those later on. Anyway, the question says, if the atmospheric pressure is 0.97 atmospheres, what is the pressure of the enclosed gas in the left arm of the tube in each of the cases below? So basically, in each of these cases, you have a gas which is trapped in the left arm of the tube. So you have a gas that is trapped here, a gas that is trapped here, and a gas that is trapped here, right? So the question is asking for the pressure of the gas in each case, right? Now, in the case of the first one, we're going to assume that this is a vacuum where the pressure is equal to 0, right? So therefore, basically, the pressure that the gas exerts on the surface here would be equal to the mercury levels differences between either side of the U-shaped tube. In other words, the pressure of the gas would be equal to 45 millimeters mercury. And that's it, right? So that's, the simplest of these 3, right? Now for the next one, it's a bit more complex because now this side of the tube is open to the atmosphere. So not only do we have the pressure of the gas being exerted on this surface here, we have the pressure of the atmosphere or the barometric pressure, I'm going to call it P bar, acting on the surface exposed to the atmosphere, the open end, all right? Now, based on the mercury levels here and here, we can come to the conclusion that the pressure exerted by the gas here would be greater than the pressure exerted by the atmosphere here, right? And that's because the mercury level here is higher compared to the mercury level here. So the question is, what's the difference between the two? And that difference would be the H, represented by the height difference between the 2 mercury levels on either side of the U-shaped tube. So therefore, we can write down a relationship between the pressure of the gas, the barometric pressure, and H, right? And that would be the pressure of the gas would be equal to the barometric pressure plus the height of the mercury, the difference in the height of the mercury levels between the 2 tubes, right? So the question is asking for the pressure of the gas. So we will write down that the barometric pressure, which is, what was it again? 0.975, I think it is. Right? Hold on. these. Okay, so. It's 90.975. And this would be atmospheres. Plus H, which is 78 millimeters mercury. Now, these two have different units, so you cannot add them. So what you'd have to do, or you cannot add them directly, I should say. So what you need to do is either convert the atmosphere unit to millimeters mercury or vice versa. So I'm going to choose to convert the 0.975 atmospheres to millimeters mercury. And if you recall, I said that 1 atmosphere is equal to 760 millimeters mercury. So I'm going to do that calculation now. So that's 0.975 times 760, and I got 741 millimeters mercury. So I'm going to put 741 millimeters mercury down here, and I'm going to add it to the 78 millimeters mercury. And according to my calculation, when I add 741 to 78, I got 890 millimeters mercury as the pressure of the gas in the enclosed part on the left side of this U-shaped tube. Okay, and that's basically how that is done. All right, any questions about this? Any questions? Any questions? Any questions out there in Zoom? Any questions out there in Zoom? Okay, so let's look at the third U-shaped tube to the extreme right in this diagram right here. So again, you're going to have your gas trapped in this side here, and that gas will exert a pressure on the surface here. You'll also have the barometric pressure, P bar, exerting its pressure on the surface of the mercury on the other side, right? And the difference in the mercury levels, the height difference between the two mercury levels on either side is 67 millimeters, which represents the difference in pressures, right? So based on the fact that the mercury level here is higher than the mercury level here, we can say that P bar is greater than PG, right? And the difference would be the 67 millimeters mercury. So we can write down the relationship as P bar is equal to PG plus the H, right? And in this case here, the pressure of the gas is what we're trying to find. So I'm going to rearrange this to get PG is equal to P bar minus H, right? Now P bar we calculated earlier as being equal to 741 millimeters mercury. And we're going to subtract from that the height difference between the two mercury levels, which is 67 millimeters of mercury. So let's see what that gives. 741 minus 67. And according to my calculation, this works out to equal to 674 millimeters mercury. Oops. Okay, 674 millimeters mercury. All right. Okay, any question about this one? Any questions? All right, so if there are no questions about that one, let's move on to question number 3. Let me clear this first. Okay, so the first question on that page is asking what is the pressure of a gas if you compress the gas from its original 500 mil at 3.4 torr to a volume of 302 mils. So based on the information provided here, the law that should come to mind is Boyle's law. And just to remind you of what Boyle's law says that PV is equal to a constant, or another way of stating it, which is what we're actually going to use in this question, P1 V1 is equal to P2 V2. All right. So what the question has given you, it has given you V1, P1, and V2. And the question is asking for the P2. Right? So I would rearrange this equation to get P2 is equal to P1, V1 over V2. And then put the numbers in. So P1 is 3.4 torr times V1, which is 500 mils, divided by V2, which is 302 mils, and you work that out, right? So that's 3.4 times 500, and then divided by 302. And according to my calculation, and in this case, I have to round down to 2 sig figs. So the answer is going to be, according to my calculation, 5.6 torr. And you'll note that the milliliter units will cancel out here and here. So that's why we have the torr units as the remaining unit. And let me just say, when it comes to using the Boyle's law, and if you have had me in introductory chemistry, you should remember me saying this. When it comes to the use of Boyle's law, it doesn't matter what the units of pressure and volume are, as long as they're the same on both sides, right? So the units of pressure, P1 and P2 should be the same. The units of volume, V1 and V2 has to be the same, right? And the reason why I mentioned that is that you could be given a question where P1 would be given in one unit and P2 would be given in another unit. So what you'd have to do is do some conversion. You either convert the P1 to the P2 units or vice versa before you plug them into the equation and then solve the answer, right? Okay, okay, any questions about this one? Any questions? Any questions? All right, let me clear this. And scroll down to number 4, which says, at what temperature will a gas be if you allow it to expand from an original 456 milliliters at 65 degrees Celsius to 3.4 liters? So the law that comes to mind when it comes to this particular question is Charles' law, which is V1 over T1 is equal to V2 over T2. Now, let me just say something about this equation. Again, as in the case of Boyle's law, it doesn't matter what the units of V1 and V2 are, as long as they're the same. However, when it comes to the temperature units, those temperature units have to be expressed in Kelvin, right? So if you're given a temperature in Celsius, as is the case here, then you have to convert that to Kelvin. In fact, let me do that now. So 65 plus 273 is 338 Kelvin. All right. So whenever you're using this law, the temperature values have to be in Kelvin. I went through a discussion as to the reason why in the videos. So make sure that you watch that again, if just in case you don't remember the reason why. All right. So in this case, they gave you V1, T1, and V2, right? And the question is asking for T2. So in this case, what I would do is to get T2, you could do cross multiplication. You're going to get, let me do it here, you're going to get V1, T2 is equal to V2, T1. And then now to get T2 by itself, you divide both sides by V1 here and here. So the V1s will cancel out. So the equation that you're going to work with is T2 is equal to V2, T1 over V1. And then you put the numbers in, right? So the volume that you're given for V1, I'm sorry, for V2 is 3.4 liters times T1, which is 338 Kelvin. And then we divide all of that by V1, which is 456 liters. Now here we have another problem because we have the volume here in liters, we have the volume down here in milliliters, so you have to do some conversion. You either convert the liters to milliliters or vice versa. I'm going to choose to convert milliliters to liters. So to do that, I'm going to put 1 liter here, 1,000 milliliters down here, and that should take care of that. So in terms of units canceling out, the liters will cancel out here and here, milliliters will cancel out here and here, and you're going to end up with your final answer in Kelvin. So 3.4 times 338, and then I'm going to divide by 456 times, or divide by 1,000. So according to my, this I have to round off to 2 sig figs. So according to my calculation, the answer becomes 2.5 times 10 to the 3 Kelvin. All right, and that's it. Okay, any questions about this one? Any questions? Okay, number 5, they gave you for a gas the number of moles, the temperature, and the pressure, and the volume. So which law comes to mind based on the information provided here? What law would you use? Anybody? What law do you think you should use in this case? They gave you the moles, which is N. Write this here. This is N. They gave you the temperature, which is T, which by the way, you have to convert to Kelvin. Let me do that now actually. 87 plus 273. So this works out to 360 Kelvin. All right. They gave you the pressure. And they gave you, and they're asking for the volume. All right. So which equation ties in the moles, the temperature, the pressure, and the volume? There's one equation that ties in all of these different terms. Can anybody tell me one thing? I'm sorry?
NRT over V.
Okay, that's one way of doing it. The more popular way of expressing it is PV is equal to nRT. Right? But you're right in terms of what you need to rearrange it to, because the question is asking for V, right? So V is equal to nRT over P, all right? So just to remind you, this equation is called the ideal gas equation. This equation shows you the relationship between the pressure, the volume, the number of moles, and the temperature. And again, the temperature must be expressed in Kelvin, and the R value is, as I said before, 0.0821 liters atmospheres over mole Kelvin, all right? So we put the numbers in. N is 0.56 moles times R, which is, as I said just now, 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 360 Kelvin, and then we're going to divide all of that by the pressure. Now, the pressure they gave you is 569 torr. Now, because we have atmospheres here, we have to convert the torr unit to atmospheres. So we're going to put 1 torr down here and above 1 atmosphere in this conversion factor, right? And then we have to crunch the numbers. So let me do that now. 0.56 times 0.0821 times 360, and then I'm going to divide all of that by 569 divided by 1,000. Wait, what am I saying? This should be 760. Okay, let me do this over again. This should be 760 torr. Okay, so let me do this again. 0.5 times 0.0821 times 360, and then I'm going to divide that by 569, which is divided by 760. Okay, so according to my calculation, now I need to round this off to 2 sig figs. So according to my calculation, I'm just going to write this here. This will be equal to 20 atmospheres. All right, and I have to round it off to 2 sig figs because of this right here. And just to show you how the units will cancel out, the mole units will cancel out here and here, Kelvin will cancel out here and here, the liters unit, oh, my bad, that should be liters, not atmospheres. Let me correct that. That should be liters. Right? So, as I was saying, the torr units will cancel out here and here, the atmosphere units will cancel out here and here, so the only unit remaining would be the liters unit, and that's basically how that is done. All right. Any questions about this one? Any questions? Any questions? Any questions out there in Zoom? Any questions out there in Zoom? Okay, let me clear this and scroll down. Okay, so this question says, you have a gas at 453 millimeters mercury with a volume of 700 mils and a temperature of 25 degrees Celsius. What will the temperature of the gas be if you change the pressure to 278 millimeters mercury, all right? So in this case, they gave you the initial pressure, so I'm going to call that P1. I'm going to call this V1, all right? I'm going to call this T1. I'm going to call this P2, and the question is asking for T2. All right. Now you'll notice in this question here, there's no V2, right? So basically there's no change in the volume. V1 equal to V2. All right. So the question now becomes, what's the relationship between all these terms? And that would be, again, another equation you would have met before. P1, V1 over T1 is equal to P2, V2 over T2. In other words, the ideal gas equation. Now, because V1 is equal to V2, that makes life a lot easier for us. All we have to do is cancel out V1 and V2 because they're equal to each other, all right? So that simplifies the equation to P1 over T1 is equal to P2 over T2, all right? Now, the question is asking for what? It's asking for T2, right? So we would have to rearrange this to get T2, and when you do that, you're going to end up with T2 is equal to P2 over P1 times T1. And therefore, all we have to do from here is plug the numbers in. So for P2, that would be 278 millimeters mercury. For P1, I'm sorry, for T1, that would be 25 degrees, which when converted to Kelvin would be 298 Kelvin. So we're going to multiply by 298 Kelvin. And then we're going to divide all of this by P1, which is 453 millimeters mercury. And then we do the number crunching. So 278 times 298 divided by 453. And according to my calculations, when rounded off to 3 sig figs, this becomes 182. And the final unit would be Kelvin. 182 Kelvin would be the answer. All right. Any question about this one? Any questions? Any questions? Okay, moving along. Here it is. Okay, so this is asking for you to calculate the density. Let me see what else is asked them. Okay, some different things, density and molar mass mainly, all right? And there's a formula that is derived from the ideal gas equation, which allows you to calculate the density of a gas. And that equation, I discussed this in the video as well. That equation is density is equal to P times uppercase M divided by RT, all right? So B is a density. P is the pressure. M is the molar mass. And T is the temperature in Kelvin. All right? And of course, we know what R is. R is a molar gas constant, which doesn't change. All right? Okay. So basically, we can apply this equation to answer this question. The question is asking for the density. It gives you the pressure. It gives you the temperature, which again, you have to convert to Kelvin. So let me do that now. So 35 plus 273 is equal to 308 Kelvin, 308 Kelvin, all right? So we have the pressure, we have the temperature. So we have P and T. We're not given the molar mass directly, but you can calculate it from the molecular formula. And let me do that now. In fact, we need my molar mass calculator, of course. So the molar mass of SO3 is 80.06 grams per mole. So So I'm gonna put here M is equal to 80.06 grams per mole, all right? So to calculate P, that would be equal to the pressure, which is 0.96 atmospheres, times M, which is the 80.06 grams per mole that we just looked up, divided by R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 308 Kelvin. So let's see what that gives. 0.96 times 80.06 divided by 0.0821 times 308. And according to my calculation, now in this case, I have to round off to 2 sig figs. So this becomes 3.0. And in terms of the units, the atmospheres will cancel out here and here. The Kelvin will cancel out here and here. The moles will cancel out here and here. So you're going to end up with 3.0 grams per liter. And that's it. That's how you do that one. All right. Any questions about this one? Any questions? Any questions? Any questions out there in Zoom? Okay, so let's go to the next question. Here it's first, which is asking for the same thing, for the same gas, but under different conditions, under STP conditions, right? Now, there are two ways of doing this. There's a longer way and there's a much shorter way. Let me show you the shorter way. The key to answer this question the shorter way is what is stated here, under STP conditions, right? We all know what STP stands for, right? Standard temperature and pressure, where the temperature is equal to 273 Kelvin and the pressure is equal to 1.00 atmospheres. And what you should know about all gases under STP conditions is that they all have a molar volume of 22.4 liters per mole. Right? The molar volume is the volume per mole of a gas, right? That will be equal to 22.4 liters per mole, right? So this is the number that we're going to use to do it the easier way, because to find the density, all we have to do is take the molar mass and divide it by the molar volume. The molar mass we saw earlier was 80.0, what was it, 80.06? Was that the molar, 80.06 grams per mole? And we simply divide it by the 22.4 liters per mole, and that's it. So 80.06 divided by 22.4, and according to my calculation, when rounded off to 3 sig figs, the answer becomes 3.57 grams per liter, because the mole units will cancel out here and here. So that's the shorter way of doing it. All right. The longer way of doing it, if you're interested, is using the same formula I showed you earlier, right? Using the same formula here. Density is equal to PM over RT, right? And what you'd have to do is put in, for pressure, you put the 1 atmosphere here, the molar mass would go here, R would go here, and the temperature would be 273, right? If you put all those numbers into that equation, you're going to get the same result. You can try it at home, but you're going to get the same result, right? But of course, it's a longer way of doing the same thing. All right. Okay, any question about this one? Any questions? Any questions? Okay, in the case of C, the question is asking for the molar mass of a gas if the density is 3.67 grams per liter, and it gives you the temperature and the pressure, right? So the formula that comes to mind is molar mass is equal to MRT over PV. Another way of stating this is molar mass is equal to BRT over P, because M over V is the density, right? So these are two ways of doing the same thing. I'm going to use this one directly because this question gives us a density, which is 3.67 grams per liter multiplied by 0.0821 liters atmospheres over mole Kelvin. And then the temperature is 15 degrees. So 15 plus 273. So this is 288 Kelvin. times 288 Kelvin. And then we divide that by the pressure. Now the pressure is given in torr units. So we have to convert that to atmosphere units. Right? And that's basically the setup. So now we have to do the number crunching. 3.67 3.67 times 0.0821 times 288, and then I'm going to divide all of that by 825, which is divided by 760. And according to my calculation, now this I have to round off to 36 figs. So the answer I got, I'm going to do it down here, is equal to 79.9. 79.9. And the units here, okay, let me show you how we get the units. The liters will cancel out here and here. The atmosphere units will cancel out here and here. The Kelvin will cancel out here and here. Torr will cancel out. Atmospheres will cancel out. So the answer would be given in terms of grams over moles. And that would be the final answer. Okay, any questions about this? Any questions? All right, let me clear this here. Scroll down to D. So D is asking for the molar mass. So we're going to use the same equation I showed you earlier. They gave you the mass in grams, they gave you the volume, they gave you the pressure, they gave you the temperature, right? So the equation that we're going to use, as I said, is the same equation. B is equal to MRT over PV, all right? Now let's see what we need to plug in. So M is 4.40 grams times R, which is 0.0821 liters atmospheres over mole Kelvin, times T. Now T is 41 degrees, which we have to convert to Kelvin. So 41 degrees turns out to be equal to 314 Kelvin, right? So multiply by 314, and then we divide by P. Now P is given in torr. So what we have to do is convert to atmospheres. 1 atmosphere over 760 torr. All right? And then we have to multiply by the volume. And the volume is 3.5 liters, 3.50 liters actually. And that's the setup, right? So let me do the number crunching. 4.4 times 0.0821 times 314. And then I'm going to divide that by 560, which is divided by 760, which is multiplied by 3.50. And then according to my calculation, now, in this case, we have to round off to 2 sig figs. So when we do that, the answer becomes 44 grams per liters. And the reason why it's grams per liter is because the Kelvin units will cancel out here and here. The liters unit will cancel out here and here. The torr units will cancel out there and there. Atmospheres will cancel out there and there. So after canceling out all the other units, the only units remaining will be grams over mole. So this will be grams per mole. And that's it. All right?
I'm gonna be 2 sig figs.
Because of the 560 here.
Oh, okay.
Yeah. Okay, any other question about this one? Any other question? Okay, moving along. Whoops, let me clear this first. Oops. All right, scrolling down. Okay, now this one deals with a law. Actually, hold on, let's see. That's the question. This has to do with a law known as, well, there are 2 laws, in fact. One is the ideal gas equation, and the other one is Okay, I'm confusing myself. Actually, this has to do with this equation right here. M is equal to PV over, hold on. I'm not confusing myself. This equation, molar mass is equal to MRT over PV, all right? Now, what we have to do in this case, because the question is asking for the partial pressure of each component. So what we have to do is rearrange this equation to get P on one side equals to everything else, right? So when you do that, when you rearrange this equation here, let me just write it down here, you're going to get P is equal to MRT over uppercase MV. Now, I should have stressed this. I know I stressed this in the video, but let me say it now. Please, and this is a common error that students tend to make when using this equation. Please do not confuse lowercase m with uppercase m, right? Lowercase m is the mass, right, in grams. Uppercase m is the molar mass, which is given in grams per mole. So make sure that you don't confuse those two, all right? Okay, so basically, you're going to apply this equation to each of these gases, the 3.50 grams of nitrogen, the 2.15 grams of hydrogen, and the 5.27 grams of ammonia, right? The question also gave you the temperature and gives you the volume of the mixture, which is 1 liters, right? So let me start off by doing the calculation for the nitrogen. So the partial pressure of nitrogen would be the mass of nitrogen, which is given as 3.50 grams times R, which is 0.0821 liters atmospheres over mole Kelvin times the temperature. What's the temperature? 25, which is the same thing as 298 Kelvin, multiplied by 298 Kelvin, and then we divide all of that by the molar mass of nitrogen. So the molar mass of nitrogen, that's 2 times 14.01. So that works out to be 28.02 grams per mole. And then we multiply by the volume, which is 1.00 liters. And that's basically the calculation that you're going to do, not only for the nitrogen, but for the hydrogen and the ammonia. So let me just do this number crunching here. 3.50 times 0.0821 times 298. And then I'm going to divide all of that by 28.02 times 1. So that equals to, according to my calculation, 3.06, and the units would be atmospheres, because the gram units will cancel out here and here, the moles will cancel out there and there, Kelvin will cancel out, liters will cancel out, so the only unit remaining would be the atmosphere unit, right? And basically, it's the same calculation that you would do for the hydrogen and the ammonia. So in the interest of time, I'm going to leave you guys to do those calculations on your own. But basically, it's the same process as I just showed you here, right? You're going to use this equation here and then plug in the numbers. In fact, the only different numbers that you're going to use would be the mass and the molar mass of the different gases. So like, for example, in the case of hydrogen, you're going to use 2.15 grams for the mass, and for the molar mass, it would be hydrogen, which is 1.08, so it's going to be 2.016 grams per mole, and so on and so forth, right? So I'm going to leave that for you guys to do. If you have any problems while doing it, please feel free to contact me, and I'm more than willing to help you out, all right? So I'm just going to move on to question number 9. Let me clear this here. And question number 9 now, let me see here, continue. Okay, so this one is a combination of 2 laws that we'll be employing in this question. One law is one that we discussed earlier, which is Boyle's law, right? P1 V1 is equal to P2 V2. But there's another law known as Dalton's law. which deals with gaseous mixtures, right? So according to Dalton's law, the total pressure of a mixture of gases will be equal to the individual partial pressures of the gases. So PA plus PB plus PC, all the way to whatever the other remaining gases are, all right? So basically what this law is saying is that if you have a mixture of gases in a container, each gas will exert their own pressure independent of the other gases, all right? And therefore, the total pressure of the gaseous mixture would be the simple sum of the pressures of all the gases in the mixture, all right? Now, according to this question, we have one container which has a volume of 1.23 decimeters cubed, and the pressure of the gas in that container is 3.24 atmospheres. And then we have some other values for container B and container C, all right? And then it says, if all the gases were forced into a fourth container, B, which has this volume, what is the pressure of the gaseous mixture in container B, all right? So the way I would approach this problem is that I would calculate the values of the pressure of each gas when you transfer the gas from their respective containers to container B, all right? So I would say for gas A, right, the final pressure, which is P2, is going to be P1, which is 3.24 atmospheres, and V1, which is 1.23 decimeters cubed. So 3.24 atmospheres times 1.23 decimeters cubed, right? And then I divide by the total volume of the container in B, which is 1.51 decimeters cubed, all right? So let's see what that gives. 3.24 times 1.23, and then divided by 1.51. And according to my calculation, this works out to be equal to 2.64 atmospheres, because the decimeter cube units will cancel out here and here, all right? So that's for the gas that was in container A, and I'm going to do a similar calculation for the other gases in containers B and C. So for gas B, P2 will be equal to 2.82 atmospheres multiplied by 0.93 decimeters cubed, again divided by the total volume, which is 1.51 decimeters cubed. And let's see what that gives. 2.82 times 0.93, and then divided by 1.51. And according to my calculation of this time, I have to round up to 2 sig figs. So that will be 1.7 atmospheres again, all right? And then I'm going to do a similar calculation. I'm going to see if I can squeeze it in over to the right here. For gas C, right? P2 is going to be equal to 1.21 atmospheres times 1.42 decimeters cubed divided by the same 1.51 decimeters cubed. And let's see what that gives. So 1.21 times 1.42 divided by 1.51. And according to my calculation, this is rounded off to 3 sig figs, so 1.14 atmospheres, because again, the decimeter cube units will cancel, all right? So basically we have calculated the pressure of each gas when placed into container D, right? So we got 2.64 atmospheres, we got 1.7 atmospheres, we got 1.14 atmospheres. So therefore what we need to do now is find the total pressure. And that's where this law comes in, Dalton's law. So the total pressure is going to be equal to the sum of these three. So that would be 2.64 atmospheres plus 1.7 atmospheres plus 1.14 atmospheres. So let's see what that gives. 2.64 plus 1.7 plus 1.14. And according to, oh no, in this case I have to round off to 1 decimal place. So the answer, the final answer is 5.5 atmospheres. And that's how that is done. Okay, any questions about this one? Any questions? Any questions? No questions? Alrighty. Number 9. Oh, let me clear this first. Number 9. Let's see what number 9 has to offer. Okay, now this one is interesting. You have a mixture of gases that is made by connecting two flats. One has a volume of 7.5 liters and 2 atmospheres of nitrogen. The other flask has a volume of 13.0 liters and 1 atmosphere of hydrogen. All right, so when it comes to questions of this type, when you're describing a setup, I like to use a diagram so that I prefer to see, what we're working with. So I apologize for my lack of artistic skills. I'm not skilled in drawing anything. I'm just going to do a rough. So let's say these represent your 2 flasks, right? And let's see here. One flask contains nitrogen and the other flask contains hydrogen, right? So let's say there's a stopcock separating those two. And let's see the numbers for nitrogen. 7.50 liters and 2.00 atmospheres. That's for nitrogen. For hydrogen, it is, oh, you know what? Let me make it according to the size that I've drawn here. So I'm sorry about that. I apologize. Let me see here. This is 7.50 liters and 2.00 atmospheres, right? And this would be nitrogen. And then in the case of hydrogen, it is 13.0 liters and 1.00 atmospheres. All right. Okay. So basically, this is the setup. And then let's say you're able to open this up, right? So all the gases will basically fill the entire apparatus. All right. So the first question is asking, what is the final volume of each gas? Well, that's very simple, right? You just simply add these two. All right. So that final volume would be equal to 7.50 liters plus 13.0 liters. So that will be equal to 20.5 liters. All right. So that answers that question. All right. Okay. No problem there. We scroll down here to get to the next question, which says, what is the partial pressure of each gas? And I presume that the question is asking for the partial pressure of each gas upon mixing. Well, this is where, let me just erase this here. This is where Boyle's law will apply for each gas. All right. So let's focus on the nitrogen first. So for nitrogen, P2, which is the final pressure, will be equal to the initial pressure, which is 2.00 atmospheres, times the initial volume, which is 7.50 liters, divided by the final volume, which is 20.50 liters, right? So let's see what that would give. 2 times 7.5 divided by 20.5. Oh, this should be 20.5, not 20.5. So, all right. Okay, and according to my calculation, I got 0.7, how many 366, so 0.732 atmospheres, because liters will cancel out. So that's for nitrogen. And then I'm going to do the same thing for hydrogen. And that is pH2, or P2, I'm sorry. Would be equal to, now in the case of hydrogen, the pressure initially would be 1.00 atmospheres, divided by the volume, which is 13.0 liters, divided by 20.5 liters. And then let's do that calculation. So that's 1 times 13 divided by 20.5. And according to my calculation, that will be 0.634 atmospheres. Again, these liter units will cancel. All right. So these are the answers in the case of B. 0.732 for the nitrogen and 0.634 for the hydrogen. All right. So that's the B part. So let me see. What is the C part asking for? C part is asking for, oh, the total pressure, well, that's easy. Right? The total pressure, PT, would be equal to what? What do you think total pressure is?
Pressure of the nitrogen, pressure of the hydrogen.
Exactly, so 0.732 atmospheres plus 0.6 34 atmospheres. So let's see what that gives. 0.732 plus 0.634. So according to, oh, wait a minute, no, I did something wrong here. 0.732 plus 0.634. Okay, so according to my calculation, this works out to be equal to 1.366 atmospheres. Rounded off to 3 decimal places. And that's how that is done. All right? Any question about this one? Any questions? Any questions? All righty. Declare this. And scroll down. Okay, now this one has to do with situations where you're collecting a gas over water. All right? And let me just say, and I think I made mention of this in the videos, this method of collecting a gas only works if the gas is very insoluble in water, right? So we're talking about gases like oxygen, nitrogen, organic gases like methane, ethane, and so on. This method is suitable for that purpose. If you're talking about a gas like ammonia or hydrogen chloride, that method will not work because those gases will simply dissolve in water, right? So this question says, you have 193 mils of oxygen collected over water on a day when the atmospheric pressure is 762 millimeters mercury. The temperature of the water is 22 degrees Celsius. How many grams of oxygen are collected? And it says here that the vapor pressure of water at 22.8 degrees Celsius is 19.8 millimeters mercury, right? Now, if you remember, if you watch the videos, and I'm assuming that you did, that there's a relationship between the pressure of the atmosphere, the pressure of the gas collected, and the vapor pressure of water. And that is given by this equation right here. The barometric pressure is equal to the vapor pressure of water plus the vapor pressure of the gas, in this case is oxygen. So what we need to do is find the vapor pressure, or I should say the pressure of the oxygen, right? The pressure of the oxygen would be equal to the barometric pressure minus the vapor pressure of water, right? So that would be equal to the barometric pressure, which is 762 millimeters mercury minus the vapor pressure of water, sorry, which is 19.8 minus 19.8 millimeters mercury. So let's do that calculation first. So that's 762 minus 19.8, 19.8. So according to my calculation, rounded out to 0 decimal places, that's going to be equal to 742 millimeters mercury, right? Now, that's the pressure of the oxygen, but the question is asking for how many grams of oxygen, right? So the equation that would come to mind is an equation that we met before, which is molar mass is equal to mRT over PV. Now the question is asking for the mass in grams. So what I would do is rearrange this to get M, and that will be equal to uppercase M PV divided by RT. And then what I would do is put the numbers in. Now the molar mass of oxygen is 32.00 grams per mole, right? Times R, I'm sorry, times P. What is P? 762 millimeters mercury. But I have to convert this to atmospheres. So I'm going to multiply that by 1 atmosphere above and 760 millimeters mercury below. All right. And then I'll multiply by the volume, which is given in milliliters. I would have to convert that to liters. When I do that, I'm going to end up with 0.193 liters. And then I'm going to divide by R, which is 0.0821 liters atmospheres over mole Kelvin, and then I'll multiply by T, which is 22 degrees, which we have to convert to Kelvin. So 22 plus 273 gives 295 Kelvin. And that's it, right? So let me do the number crunching. So that will be 32 times 762 divided by 760 times 0.193. And then I'm going to divide by 0.0821. And then I'm going to divide by 295. And according to my calculation, no, something is wrong. Let me do this again. 2 times 762 divided by 760 times 0.193 divided by 0.0821 divided by 295. Oh, that's it. Okay. So according to my calculation, the answer I got, now how many sig figs do I need? Okay, 3 sig figs. So the answer I got is 0.256 grams as the final answer. And we get grams as the final unit because the moles will cancel out here and here. The Kelvin cancel out here and here. The liters cancel out here and here. Atmospheres cancel out here and here. Millimeters mercury cancel out here and here. So the only unit remaining would be the gram unit. So that's the answer, 0.256 grams. Yes, sir.
How come you wouldn't use the 742 instead of 762?
Thank you. Thank you for correcting me on that. This here should be 742, not 762. So I need to redo that calculation. Thank you for picking up on that. 742. All right, let me redo this. 32 times 742 divided by 760 times 0.193 divided by 0.0821 times 295. So the actual the actual answer is not far from this, but still I need to correct that. So the actual answer here is 0.249. So here I'm going to put 0.249 grams. All right, thank you very much for that. Okay, any questions about this? Any questions? Any questions? All right. Okay, we have 11 minutes left. Let's see what we can do in the time that's remaining. Let me clear this and scroll down. Okay, now this one is an example of a gas stoichiometric type problem, all right? It says how many liters of ammonia at 850 degrees Celsius and 5 atmospheres are required to react with 1.00 moles of oxygen in this reaction. And it gives you the balance equation, which is necessary to solve this problem. So, basically the way I'd approach this is that since the question is asking for how much of this that is needed to carry out this reaction, I would first find out the number of moles of this using the moles of oxygen, right? And according to the question, the moles of oxygen is 1.500 moles of O2. And what I would do is convert from moles of oxygen to moles of ammonia using the mole ratio between the oxygen and the ammonia. That would be 5 moles of O2, 4 moles of ammonia, and we're going to end up with 0.800 moles of ammonia, right? So that's the first thing. Then what I would do is use the ideal gas equation to find the volume. So if we rearrange the equation, we're going to get V is equal to nRT over P, all right? N would be what we just calculated here, 0.800 moles multiplied by R, which is 0.0821 liters atmospheres over mole Kelvin times the temperature. What's the temperature? 850. So again, we have to convert that to Kelvin. So that's 850 plus 273. So this works out to be equal to 1123 Kelvin. So that goes here. And then we divide all of that by the pressure, which is 5.00 atmospheres. So let's see what that gets, 0.8 times 0.0821 times 1123, and then divide all of that by 5. And according to my calculation, now in this case, we have to round off to 3 sig figs. So that works out to be equal to 14.8 atmospheres. All right. And that's how that is done. Any questions about this? Any questions? Any questions? Yes, sir.
What's the unit next to the 5 at the bottom? Like 5,
5.00? Oh, this should be atmospheres.
oh, okay, thank you.
Okay, any other questions about this? Any other questions? Okay, let me clear this here and see what next. Okay, I'm gonna leave B for you to do, again, in the interest of time. But if you understood what I did in the A part, then you should be able to do the B part. Again, if you have any questions while doing it, please feel free to come. Or email me, whatever. All right, the next question has to do with another gas law, which is known as Graham's law of diffusion. All right, and there are several ways of expressing this law. The way that we would use in this particular question is in the form of this equation right here. The rate of diffusion of gas 1 divided by the rate of diffusion of gas 2 is equal to the square root of the molar mass of gas 1 divided by the molar mass of gas 2, right? So that's basically what the Graham's law of diffusion is all about. Basically, fusion is the process of a gas escaping from a container through a tiny hole into a vacuum, right? And I discussed all of that. There's another equation which deals with the root mean squared speed of a gas that will be equal to the square root of 3RT over M, all right? And in this particular case, the R value that you're going to use will be 8.31 joules per mole Kelvin, right? Now, I don't think I have a question using this equation here, but this equation here is actually related to this right here, all right? That's the reason why I'm mentioning. But let me just check something here. Give me a minute. Let me just quickly check the rest of this here. Okay, so unfortunately, I don't have any questions here using the root mean squared equation. But I am quite sure I did at least one example in the video, so you may want to check that out. All right, in any case. So as I was saying, the R value here is this, and if you plug the number here into this equation, the root mean squared units will be in meters per second. All right. So when you're looking at the example that I've done in the videos, you're going to see how that works out. So let me get back to answering this question. Now, let me clear this here, or not clear, but there is. Okay, so when it comes to questions like these, you have to make sure that you interpret it correctly. And again, this is one of those questions where students tend to make errors, all right? Okay, so as I said before, this is the equation that you're going to use, this equation right here, all right? So you have to be careful when using this, you have to identify the different terms and plug them into this equation. So according to the question, it says, in an experiment, it takes an unknown gas 1.5 times longer to diffuse than the same amount of oxygen gas, O2. Find the molar mass of the unknown gas, all right? So what this question is saying is that the rate of diffusion, and by the way, again, I think I covered this in the videos. A lot of textbooks confuse diffusion with effusion. Those are two different things, all right? And I won't go into the distinction between those two because I've already described that in the videos. So go back and watch the videos if you're not sure about the difference between the two, right? So But in a lot of textbooks and chemical literature, people tend to use diffusion as if it means the same thing as a fusion, but they're not the same thing. And that's the reason why the law is called the Graham's law of effusion, all right? Not diffusion. All right, so according to this question, the unknown gas has a rate of effusion which is 1.5 times longer than oxygen. So this is how I represent that. The rate of effusion of the gas is equal to 1.5 times the rate of effusion of oxygen, which means that the rate of effusion of the gas divided by the rate of effusion of oxygen is equal to 1.5. Now, according to this law here, we can also add to this side of the equation that 1.5 is equal to the square root of the molar mass of the gas, oxygen, divided by the molar mass of the unknown gas, right? And the aim is to find the molar mass of the unknown gas. Now, one thing you should have learned in your math courses is that if you want to get rid of the square root sign, what do? You square both sides, right? So if you square both sides, you're going to get 1.5, should be 1.5 squared is equal to MO2 over mg. The aim is to find mg, so mg is equal to MO2 over 1.5 squared. And the molar mass of oxygen is 32. What's going on with this thing? All right, so this is going to be equal to 32.00 grams per mole divided by 1.5 squared. So 32 divided by 1.5 squared, and according to my calculation, rounded off to 2 sig figs, this becomes equal to 14. This thing's just not cooperating. 14 grams per mole. I have a funny feeling I did something wrong. Let's see here, 1.5. Okay, yes, it's correct. All right. So that's basically oh, I realized the mistake I made. I have to go right back up to this point here, right here. I'm sorry, folks. I apologize for this. And this is where, as I was saying before, you have to be careful when reading the question. You know what? Let me just clear everything. I apologize. I'm going to rewrite the equation here. R, what was I saying? RG over RO2 is equal to the square root of MO2 over mg, all right? Now, here's where the mistake I made, and it's a common mistake that is made all over. Right here, it says that the unknown gas diffuses 1.5 times longer than the same amount of oxygen gas, right? And this underscores the importance of recognizing the difference between the rate of anything, in this case, the rate of effusion, and the time it takes for effusion, right? The rate deals with how fast the process is. The time, right, or how long deals with how much time it takes, right? And there's an inverse relationship between the two, right? So I can add another piece right here, which says that the time of effusion of oxygen is divided by the time of effusion of the gas is equal to all this, right? Because of the inverse relationship between the rate of effusion and the time of effusion. So it is on the basis of this that you're going to find the molar mass, right? So how am I going to do this now? So basically, this part here, because the unknown gas diffuses 1.5 times longer compared to oxygen, I'm going to put 1 over 1.5 here, right? Right. Because the time of effusion here is 1.5 times that of the oxygen. So now, to find the molar mass, we're going to square both sides again, but this time it's going to be MO2 divided by mg is equal to 1 over 1.5 squared. Okay. 1.5 and all of that will be squared. I'm sorry, folks, for some reason, this thing is not responding whenever I try to write something. Let me try this again. 1 over 1.5 squared, right? So the aim is to find mg, the molar mass of the gas. So mg is going to be equal to 1.5 squared times MO2. So that would be 1.5 squared times 32.00 grams per mole. Okay, and 1.5 squared times 32.00. So that rounds up to 72 grams per mole. And that's it. All right. I'm going to leave the rest of this for you to complete. All right. And again, if you have any issues while doing it, let me know. While I'm at it, let me set up a Dropbox for this. Let me clear this here. So this would be assignment number 5, I think. Okay, so I'm going to give you until Friday to do it, to complete it, to submit it. Let me see it. So, no, I made a mistake. Hold on. I should do this. And this now will be. 27. Okay. So now you should be able to upload your assignment in Canvas by that date. Again, make sure that you do it in ink, make sure that it's submitted as a PDF document. Make sure that you write all your names on top of each page. I think that's all I have to say for now. All right. All right, so that's it, folks. I'll see you guys next Tuesday.
When is the next test?
I'll have to look it up. Give me a minute here. Let me just do a quick posting of base class in audio section. Today is 2/24/26. Oh, I put the wrong year here, but anyway, okay, so let me go to the syllabus. Okay, what do we have here? All right, so according to this, the next test should be March 23rd. All right, so the first test, we're testing on what, chapters 1 and 2?
Yeah.
Okay, so definitely 3, 4, and 5. I'm not sure yet about 4. I mean, I'm not sure yet about 6, so. So 3, 4, 5, definitely. Will be on test number 2. All right, okay, sorry.
Sorry, I don't interrupt. Would you be uploading a, like an example test from previous semesters for this upcoming?
I think I may have, let me check and make sure, I think I may have done that already. Okay, so. Let's answer keys. Okay, so you see this one right here?
Yes, sir.
This has test 1 through 3.
Okay,
So you should be able to identify problems based on what we have covered. Just look up in that document, just look up for test number 2.
okay,
That should be it,
wonderful, thank you so much.
all right?
When do we find out what we got on exam 1?
Good question. I hope to have that done graded by Friday. By this
Awesome.
Friday,
Awesome, thank you.
all right? Okay, so you guys out there in Zoom, I am signing off.